real great. Okay, it is my real great pleasure to introduce Professor Ning Lu, who is going to give us today's seminar on lead seminar on challenges and opportunities in the changing electric power systems. I think she's been very, very active in and her group there in North Carolina. I think they've been on the leading edge, in particular on the links with power electronics also and power systems. So please welcome Professor Lu, and then we will try to have the presentation, and then only if there's some clarifying questions, please raise your hand. But otherwise, do put your questions as we go through, do put them in the chat. And then after the presentation, formal presentation is over, we can go through the questions and comments. And so we like to make it interactive. So please welcome Professor Lu. Ning, it's all yours. Okay.
Okay. So you can see my slides now, right?
Yes.
Okay, great. Thank you, Maria. It's very kind of you to introduce me to this group and then invite me to this seminar series. Here, I also invited some of my students over. In case that you have detailed technical questions, they will stay here to answer that as well. So I'm going to, let me see. First, I want to thank the funding agency. Most of this research has been funded by Department of Energy. And you can see that we have many industry partners who contributed to this as well. Our data are mainly from New York Power Authority, Strata Solar, Electricity, Wilson Energy, New River, Latin Power, and Renault. So you can see that these are co-ops and munis. So our smart meter data are mainly from them. And then our PV data is mainly from Strata Solar. Our transmission network model mainly from New York Power Authority. So these are the postdocs and PhD students who are working on it. And those are the PhD students graduated already. But most of these publications are made by them. I have listed these publications here for the topics I'm going to present today. So in case you want to know the technical details, then you can go over them. So today I'm going to first give an overview for the PARS platform we're developing, mainly what's the configuration of it and what's the design considerations. We took a digital twin-based approach. I think this is unique. And then I want to present why we do so, and then what are the design considerations. And then I want to present the 3 key technologies support this PARS platform, to support this digital twin based approach. I know that Maria also worked in this area, and then I hope that in the audience, most of you have the same interest, so we can collaborate in the future. I provided enough references for technical details. I'm going to put more emphasis on synthetic feeder topology generation. We do have this low profile super resolution method. I'm going to just touch the surface of it. That article is just being published, so I will leave that to the future. And then I'm going to present this meta learning based focusing method. Again, we have a TCM based method. I'm not going to present that in detail today. For the modeling part, I'm going to basically introduce the dynamic modeling of microgrid using a co-simulation platform. What are the modeling approach, and then how we coordinate different type of control, how we actually do this asynchronized modeling. So I'm going to basically go over each of these real quick, and then I'll conclude this presentation. So first, let me give you an overview of the PARS platform, because this is the motivation that we develop these key technology. So first, we were asked to develop a photovoltaic analysis and response support platform. And then in our vision, this should be a comprehensive simulation platform. Because our project is mainly supported by the DOE RE CETO office, so they have a strong interest in integrating PV at all levels, meaning from the rooftop PV system, which is only a few kW, to megawatt level PV system, a few megawatt or up to 50, 80 megawatt, which is integrated in the GAN-based method, trying to, let me see here. This is what we're doing. I think this example will be really helpful. In image processing, when you have a blurred image, you can use this super resolution method to recover the high resolution image. So this is the idea behind that paper. What we're trying to do is to have this 15 minutes or 30 minutes data, and then we can recreate 1 minute or 5 minutes high resolution load profile. So this is the first GAN-based model we're developing. By doing so, what we can do is to actually using these available data sets and then use a super resolution to recover these high resolution data to use for the Power Platform. So the other one we are mainly interested in is for load profiles. Even though we don't have real, we don't have synthetic data sets, we have enough smart meter data to start with, because we have like 8,000 from one utility, like 8,000 from another utility. The needs for us to use synthetic data sets is low. So we figured maybe the next stage is to develop a method so that we can actually generate the feeder topology. We did a quick literature search and we didn't find anybody doing that at this time. So basically our idea is to use this GAN-based approach. We have a generator, we have a discriminator, and then we train the generator to generate load profiles. And then we use discriminator to see whether or not the generated load profile is realistic. So by competing with each other, we can make this more and more realistic. So the first thing that we did is trying to find out what's the attributes that we should use. You can see that this is a distribution feeder. So we basically select the length of the device, meaning if there's a line, we select the length of the line, and then their amperage, because the line, the size of it basically is related with the amperage. And then we have this distance, basically how far away a device is from the feeder head. So we have this different levels. You can see this is just like tree branches. So if you go from here, this is the backbone, that's level 1. And then if you have a bifoc here, you go to level 2 and then until the finer branches. So we have these 9 levels for this different branches. So you can think about that as the finer it is, the smaller this branches would be. And then we have different phases. We have this A, B, C, because in distribution system, it has 3-phase circuit and 2-phase circuits, and then have single-phase circuit. So this is the way we trying to convert everything into a graph-based method. But we do find that the data that we have 14 realistic feeders, all same type. But this should not be is not sufficient for us to develop these. One of the GAN-based method requirement is massive data sets. So what we're doing is we do the augmentation. So we have 14 realistic feeders, but each of them, they have thousands of nodes. So what we're doing is we sample this whole feeder so that we can sample part of it and then make it a structure to start with. So basically we can generate the substructures and then we can generate the finer part of it. So this way we solve this data, insufficient data problem. But we do find that if we have more feeders, this method is readily extendable. So unlike these chemical molecule structures, our feeder has an advantage because even a substructure of it is meaningful. But for a molecule, if you only take a substructure, it may not be meaningful. So this is one of the advantages for us to do augmentation. So what we're trying to do is we also try to ignore the geographical difference, the distance So our lens mainly related with the electrical lens. The other thing we do is in order to do a direct graph, we don't use our traditional node. Like this A is a connection between node 1 and 2. Instead, for A, this A actually is a line segment. So that way we can have a nodal attributes. So each line is a segment. So this line segment is different from the parse system definition. So by doing that, we will be able to convert the feeder topology to a electrical distance plot like this, instead of have to consider the geographical coordinates. And then by using the device's node, we can easily generate this attributes matrix corresponding to the adjacency matrix. Then we can start our training. So you can see that we have the performance metrics, how we can tell whether or not a feeder is generated or is real, or how we can let the discriminator improve the generated profiles. We use basically connectivity and a phase transition. So connectivity means that we don't have these isolated nodes. Sometimes when you just begin with, you will have some isolated nodes. And then we also have the phase connections. Like, for example, the 3-phase circuit should be transitioned to 2 and 1 phase, but the 1-phase circuit cannot transition to 3-phase circuit. So we need to let machine learning that, so that the discriminator, once it sees that a 1-phase circuit connected to a 3-phase circuit, it will reject that. It will give a low score. Similarly, for AV phase, you can only be followed by a line of either phase A or phase B. It cannot be followed by phase C. So the other thing we check whether or not the generated load profile is realistic is to see if it feeds the empirical statistics. For example, for this different type of circuits inside the distribution system for different type of feeders, their ratio are follow a certain distribution. Similarly, for the length of this distribution lines, it follow a distribution. So after we generate these, we will check to see if they follow this empirical statistic. If they don't, then we will discard them. So we do have this multi-class collapse problem. So you see that if you keep on running, eventually it will generate a straight line. And then you can see the degeneration happens in the about 3,000 iterations. So what we are doing is we use the early stop to generate these reasonable feeders. So after we have that generated, we ran OpenDSS to see if this is feasible. And then we check the voltage profiles to see if the result is reasonable. So that's the GAN-based method. So to summarize that, using GAN-based model is pretty interesting approach, because this is something new to our group as well. We think that by doing this, we can use a limited set of utility data. Usually they gave you 10 or 20 feeders to start with, but with that, we can generate 100 or even thousands of similar feeders with similar load profiles. So the next, I'm going to talk about the meta learning, and those are the forecasting methods. So the reason we think of why we do the meta learning based method, load forecasting is relatively a mature technology. So we have long-term and short-term and ultra short-term forecasting method developed. However, there's an increasing need for forecasting tools, especially a more versatile and readily available forecasting tools. This is because we have integrated a large amount of variable generation resources in DERs. And then we need the forecasting at all levels, not only just at a house level, maybe 5 houses for a microgrid, or this microgrid can have 50 houses. So we need a really flexible tool to focusing what's the operational baseline. And then we also have this kind of flexibility. We need a load focus or PV focus to start with. So if we have such a digital twin, we can't each time get a forecasting task and then just let a human operator trying to decide what is the tool to use, what's the parameters. We need a versatile and automated forecasting tool. So this is the motivation for us to do that. You can see that just for our purpose, when we try to design different PV functions, we need forecasting at house level, building level, transformer level, and feeder level, or at the PV farm level. So our forecasting task can be 24-hour ahead, 48-hour ahead. And then if our the scheduling interval is 1 hour, then we need 5 minutes forecasting for the entire hour. So you can see that there are many forecasting horizon, and then we need to update this with a rolling window. So how we can do that in a more flexible way. So this is the motivation of it. So the mental learning based method basically, again, is developed in another domain like image processing. Basically, you have a different task. You can recognize, you can use the algorithm trying to recognize the cat, but the same algorithm, if you use to recognize a dog and then you develop these algorithm, can you actually port this algorithm and then let them recognize apples or oranges? Or if you have these two tasks, can these results be helpful for you to recognize a bike and a car? So similarly, if we already have a focusing task, which have 24-hour ahead and then already forecast, and then we have another one similar thing, but at a substation level. So if we conduct these tasks long enough, or we have a multiple tasks in here, can it help us if a new task are coming? So this work has been published for technical detail. You can go here, check out this paper. So basically what we're trying to do here is to see if we can actually design a group of tasks. This task in number should be large enough so that from the general, we can generalize the method we developed. So there are 3 layers: base layer, and the meta learning layer, and then the online application layer. So basically in the base layer, we try to develop different focusing tasks. Basically we use we take the advantage of the smart meter data we have, and then we generate the focus at different house level, like 1 house, 5 houses, 50 houses, and then up until like say substation level, like a few thousand houses. So by doing that, we would have a larger variety of focusing tasks. So we select different focusing models, and then these will be the training data for our meta learning layer. And then we can design these task features. So our goal is to, based on these task features, the model should tell us which model to use. So basically, you can see that these task features include the data granularity, like is it 15 minutes, an hour, a day, or month? And then what's the historical data length? And what's the focusing horizon, and then exogenous factors and low level. So if you can have this dimension input into this model should tell you that which model you should use for that purpose. So this is our goal. So by doing that, what we can do is, okay, we say, hey, here at house level, we want to do 1 hour, and then we have historical data for 1 month, and then we have this focusing horizon like day ahead, and then the temperature data is known, and then we have the load level at single user level. So it will tell you, well, this is model to use, and then we can just directly use it and then produce the focusing result. So we do have another model for PV focusing. I'm going to skip it for the interest of time. This is TCM based model. Basically, we're trying to select a detector. We have Stratus Solar gave us 100 PV sites, and then what we're doing is selecting what are the detector sites that we can use, so that we can forecast in 2 hours based on these sites, what would be the abrupt PV power drop. So basically this is used like when a cloud passing by, it will passing either from this direction, this direction, this direction. So if we can detect a correlation between sites, then we can actually improve the short-term load forecast, focusing those large cloud cost PV drops. So the last one is the dynamic modeling of microgrid by co-simulation. So this part probably most of you are interested in that, so I'll probably spend more time on this. So what we're trying to do is that eventually when we build these detailed feeder topology, make it realistic, and then we attach each node with realistic load profiles, and then we also provide our energy management system with a good forecaster at all levels. But to make this whole system realistic, the model itself is very important. As I said before, for different level of simulation, your required simulation detail is different. Your runtime is also different. So what we are trying to distinguish is which of these part of the system should be modeled by EMT, so that we use them run every few microseconds. Which part of them can be safely moved to the phasor domain and modeled every few milliseconds. So those are the work that we have been doing. We quantify by moving the system from EMT model to phasor model. What's the modeling accuracy degradation, and what has been sacrificed when you move detailed model into a phasor domain model. And then we also, by functionality, we want to see which functionality actually require us to model microsecond level dynamics, which functionality would not require us to do that. And then we studied the interaction between different layers, because you can see that the main problem for you to transit from a microsecond level simulation to millisecond level simulation is the loss of data, because when you start from here, you start to have this detailed simulation, but when you go back here, you only get the data for what happened over here is lost, and then you have a discrepancy between these two data points. And then we're going to talk about that in detail to see what's the method you can use to reduce the error caused by this time delay when you transit from one layer model to another layer. So first, we want to discuss the model complexity. You see that we need both steady state model and dynamic model. So which part of the model should be steady state, which part should be dynamic is the first thing we want to decide. And then use load as an example. CIP model is the common model that we use. A lot of the models just use a constant impedance or a constant power model. But we do have composite load model available as well. So under what kind of simulation condition we need a composite model, right? So composite load model basically is like this. It actually have not only ZIP model, it can also have a motor model and have the PV models to model the power electronics systems. But the problem of that is we not only need to derive the load composition, which is changed with the respect time of the day, but also the parameters, the different resistive load and the constant power load. What's the parameter of that? How much we can simulate for the voltage sensitivity? Those are all changing. So our question would be, do we need a model with very high model complexity, or we can have a very simple model, but update that very often through the real-time data measurement? So we can see that the problem is our load composition is varying. So this is a very data-intensive task. And then it is really hard to keep the model up to date if we have a complex model, because just the sheer number of model parameters, like for one feeder, is a lot. So what we're trying to do currently is to use a more data-driven based model to use the measurement of data, trying to derive different device level models. We have designed this for battery model, diesel generator models. If you are interested in that, those are the two papers related with it. So we do find that there's a trade-off between how even you use a data-driven model. You want a simplified model, or you want a more complex model, meaning do I just use a 1R, or I use 3R with the 1C to represent the battery circuit? And then these parameters does change with respect to SOC, the state of charge. So do we use one set of the parameter or several sets of the parameter to represent that? So those are the trade-offs you need to make. So the other thing is when we do this kind of a control, we talk about the model, but there's also a control you need to decide. So the control we're talking about, one is system level control, which actually is more energy and power management. And then its interval is like every, you schedule your energy every hour for a day ahead. And then you schedule, when you close the real time, you adjust that schedule to each hour or each 5 minutes. And then when it's close to the real time operation, you probably adjust like every minute. So those are using forecast value. But the device level controller does not have that luxury. It actually, for example, if I have a PV here, I will have a droop control. Then I use instantaneous values measured by my sensor here. And then my control interval is millisecond, microsecond to millisecond. So this is why for the device level controller, we move them to the HIL, to the Emacs scene sometimes, or ePhaser scene to model that. But the system level controller, we move them out of the HIL, and then they were simulated externally so that we can run faster than real-time simulation. These are more steady state or quasi-static steady state model. So this is our division for how to model the control part of the devices. So you can see that we develop our model usually in Simulink, and then we put them run on HIL. And then we also simulate the communication. So these are ongoing efforts. So we can model the several attacks. So we do have this HIL with TCP/IP Modbus protocols. So we can see that once a tower is down and then the connected DAR is down, what that would do to our control. But we found that this kind of a simulation will make this realistic, because a lot of these control, we can't assume them to be like OpenDSS-based approach. We send a control and then the device will receive it. In reality, we send out the control, a device may or may not receive it immediately with some delay, usually. So for the PV models that we have, I put the paper down here, and then if I highlight the names in red, that's the student who conduct this work. So they are actually in the chat box. So if you send your question in the chat box, my student could answer that from there as well. So feel free just to type in your questions now. So for the PV farm model, what we're trying to do is to design to go over the factory sheets to see what are the things that we can control. And then we go over the standards to see what are the functions that can be implemented on this megawatt level PV system. So what we are doing is, Victor is a student work on that. He developed this fast response power curtailment algorithm. So the reason we developed that is we found that a lot of our microgrid control function require us not only control the BAS system, the battery system, but also the PV, because we have very limited option capability in there. So if we use the battery only, sometimes we have to shut down the whole system because the PV does not have any capability to regulate its real power. So we developed this fast response PV curtailment method so that the PV can follow a power reference. And then we also model the startup switching logic, reactive control modes, and then the ramping capability, you can see that, and then the fault registry. So for the rooftop PV system, things are a little bit different. We can have this grid following function following the zoom, the loops, the droops. Yeah, I think I talked too much. And then when we do this, you can see this is a list of functions for the rooftop PV system. The reason we divide them by rooftop PV system and the megawatt PV system is megawatt PV system are grid scale, and then it can be directly connected to the control center through a SCADA system. But rooftop PV system are usually behind the meter and customer owned. So their controllability is minimum. So what we are doing is follow this attribute standard, trying to model their functionalities. So you can see that we basically found that if we don't model that detailed grid following function, then phasor domain simulation should be sufficient. That means we don't model this waveforms. And then we can use a much larger time step and then make the simulation a lot faster. So we also model the diesel generators. The reason we do that is because we want to study the interaction between synchronous generators and the inverter-based resources. So diesel generators in a microgrid could be valid to try to provide a little bit of inertia to the whole operation, because mainly if you have a PV powered system, you only have battery storage and PV systems. If we do have a diesel there, we want to see whether or not that they will compete each other, and then whether or not the diesel with its inertia could help or could compete against the battery control and worsen the situation. So that's the main reason we simulate the diesel with these functionalities. For the BAS system, this is the main one that we use for grid forming. So once we go microgrid operation mode, then this would be the functionality we're going to do. And then this is the grid following functions. So basically, I think a lot of people are doing that. And then we what we have done probably would be similar to others, but for the grid forming functions, we have considered that, especially this three-phase imbalance of control. Our students spend a lot of time trying to figure out how to make sure that we can supply a unbalanced system, because we focus on distribution system. And then there are a lot of PV on different phase. This can create a significant amount of imbalance between different phases. So what we need to know from the HIL team is what kind of level of imbalance their controller can handle. So they need to convert their controllability to a power and balance capability, and then send us that as a requirement, so that the energy management system knows that in their energy management system, how could they balance the loads in the PV among different phases, so that it won't bring the control system down. So that's actually lessons learned. We found that when we design this energy management algorithm, we run it on OpenDSS, everything is so perfect. But once we connect to the HIL team, and then it starts to break things down, it either run the storage at 120% of its capacity, or it just break the system down without enough ramping, or just the whole thing just fell apart. So that's why we try to connect the two kind of simulation together to see, without a field test, which this, if we don't have such a high quality digital twin of the system, we would have to rely on laboratory tests or field tests to review these problems. But right now we can, through the modeling, to do that. So you can see that to remove the imbalance, we're trying to see there are two approaches basically in field. We can either use three single-phase inverter, which is very benign to this kind of unbalanced operation, because you have three inverter to supply the load, or you have a three-phase inverter model. So this is more prone to the imbalance, and then it's heavily depending on whether or not you have a grounding transformer to actually mitigate the zero sequence current. So basically, our student Bei, she developed this alpha beta stationary reference frame. So we compared this design with the decode domain, and trying to see, as I said, we convert to this, we do the simulation, and then we generated this measurement-based approach to see what corresponding to the voltage imbalance, what's the power imbalance there. This red line is allowed imbalance level. So if you are exceeding this level, then the system can will no longer meet the operation requirement. So by doing this kind of simulation, we would be able to translate the control limitation, like a voltage imbalance, to power imbalance. And then based on the power imbalance, we can design our energy management system, trying to make sure that we do not create the power imbalance exceeding this level. You can see that if we add this system with the grounding transformer, we can effectively make the power imbalance go from, like, say 0.3 to 0.5. So this is why we have this layout. We suggest that if we have three-phase inverter, we put a grounding transformer here, and then that could allow us to supply more those with more imbalanced load. So the other distinct character we are modeling is we model the cold load pickup effect. So we have these houses. If we stop serving it for a couple of like hours, then once we turn them on, the peak load will increase. So we model the household load in detail, and then so that we can derive a performance-based model to calculate if this outage hour is say 1 hour, 2 hour, depending on that, what would be the peak value, the duration, and then the decay of that, so that we not only model this normal operation condition, but also because we model the microgrid, for example, if I have enough, I only supply one part of the feeder. And then after 3 hours, when the sun is out, I probably pick up these. But in the past, people don't consider how much load you need to pick up, because if they are offline by 2 hours, the load that you initially pick up is much higher than your original value. So this is something unique that we considered. So the last thing that I want to emphasize is the reason we are confident our model will work, because we do the benchmark. We use a full EMT model to start with, and then we move part of the network to the phasor-based model. and then see how much performance degradation would be. For example, this is our EMT model, and then this is the phasor-based model. So our EMT model will be a small part of the circuit. So if we move part of these over to this part, what would be the degradation? So you can see from here, we compared the two kind of considerations. First is we increase the communication delay between EMT and phasor domain. You can see that the more delay you have, the more deviation you will have. So you can see that this is the EMT model, the solid line, and then this dotted line are the ones that with the phasor-based domain simulation. So you can see that when you have a communication delay, what is the modeling accuracy you're sacrificing? You basically have a delay of the model. The other thing is when we have this kind of code simulation, we can use interpolation to project what the system would be in that interval. So if we use that, then it can shorten, it can make this difference a little bit lesser. So this has been published. We submitted to ASPE PS general meeting. It has been accepted. I posted the link here. This is a link to the archive that we already posted that, so you can access that for more detail. Okay, so I think I'm running out of time. So this is the last slides that I'm going to go over. Basically, we think that massive data sets are required for us to develop these control technology. But if we want to develop these technology, especially in power system setting, to use a field test or even laboratory test is prohibitively not cost effective. The cost is too high. So what we are trying to do is be able to, based on the limited set of data that generated these high quality synthetic data set that we can use and share with the research community so that our result can be reproduced. So we believe that in the future, the solution is for this community to join effort using the actual data sets we have, and then convince the manufacturers so that we can design, develop these high fidelity power system digital twins. So if each manufacturer can have a digital twin, then basically what we're trying to do, we can just integrate their digital twin into our system without knowing the inside setting. We can still run that. So this this digital twin has to be high fidelity, because if it's not, then you can't replace the lab test and the field test. And then it has to be able to model a wider range of operation scenarios. That means our real data set has to be complete. We right now only have a lot of normal operating conditions, but we don't have a lot of these abnormal operating conditions. That means that when we produce our operating conditions, we mainly produce normal operating conditions. So to scale up easily, we need a method that can standardize the feeder. So meaning we take a real feeder, we can't use that directly. We need to design a scale up, a reduced order model probably, but without sacrifice its accuracy and use in our large scale simulation. So the other thing is we need to identify what model complexity to use, and then what model parameters can be tuned either online using operational data or offline using these historical data. So if we can cover this aspect and then cover both steady state operation and dynamic response, then we can truly use this simulation test bed to develop our algorithm and validate their performance. This can also give us a level of the ground to play with, like the community and computer science. So we have standard data sets, standard, that is the platform. So all the algorithm can be compared in this kind of setting. Okay, I think this is the last of my slides. So this is my contact information. Now I'm happy to answer questions.
Thank you very much, Ning. I think it was a great presentation, sort of long, you know, end to end. What do we do with power systems? So there is a lot of synergy, as you know, with what we are doing here at MIT. So I will send you an email and we will follow up. But there are questions in chat. Maybe we should start that way. And again, I said at the beginning that officially, you know, people can, the meeting ends at, you know, at the end of first 1 hour, but whoever wants to stay and we have discussions, we can go longer. So let me start by asking Tong Huang. Tong, are you there? Maybe you want to state your question.
Yeah, I'm here. Thanks, Professor Lu. That's a very inspiring presentation. I really appreciate it. So I have two questions. The first question is about your first research topic, the synthetic distribution system. So in Texas A&M, so Professor Orby also do some synthetic grid for transmission system. I'm wondering, so what's a unique challenge of creating a synthetic distribution system compared with creating a synthetic transmission system? This is my first question. My second question is about...
let her answer the first question. Okay, yeah. So and then we go to second. Okay, Ning, go ahead.
Yeah, I follow up that research before. In my opinion, transmission system usually are unique because you have this transmission system, right? So the network topology and the data are hardly changed over the years. So if you study, say, New York Power Grid, or you study Western WECC, their topology is unique, and then they don't change a lot. So if you use realistic model to start with, that's probably a better, in my opinion, because when you do that, it gives you realistic modeling results, and then you actually have a lot of things specific tuned to the topology. But in distribution feeder, things are very different. Why we attack this problem from distribution angle? Because for each utility, you have thousands of distribution feeder out there. And then, as I said, for one distribution feeder, part of it can occur somewhere else in the same area. So that allow you to do the augmentation, because each house build, a community, they follow similar layouts. So the way they design substations are similar. So that's why when you do distribution system, you actually can reuse part of the topology again and again. And then that actually is benign to this kind of GAN-based model. So that's, I think, the main difference that we think that modeling that is probably more useful, especially when you do the distribution. You usually cannot just try one feeder topology if your method works or not. You have to try it probably on a few hundred of them to actually validate that because of the diversity in the distribution system.
So before we go to the second question, Tong, I want to clarify, Ning, the distribution systems you are simulating, are they only radial networks or you have meshed?
Currently, we only do the radial network, even for our microgrid control. Yeah.
So the question is how, I think that's a major step. That question comes always up, you know, because in Europe is different than here and so forth. So do you see in some of these learning methods that they are going to get much more complicated when we have meshed networks, or have you had any experience? Yeah, okay.
Because the mesh network will actually generate one very hard to solve the problem. The point that you mesh it is very unique. It's not like a generalized. Right. See, radio system, it just go naturally like a tree branch, right? But for mesh network, the connection point is sort of like following physics, right? So it's learnable. I think it's learnable, but again, it has to require you build enough expertise modeling this non-mesh network, and then just go to that. It definitely will have another layer of difficulty there. We tried first, but we eventually gave up that. We just started with the radio network to start with. This is a very good question.
Understood. Thank you. Tom, second question?
The second question is about your third research topic, which about the model granularity selection, right? So recently we are working on power electronic simulation from the system level. I'm wondering, so in the power electronics, you have a switching dynamics is from the PWM. I'm wondering when should we model the PWM in our simulation? When should is it sufficient just using an average model to model the dynamics for this switching dynamics?
Very good question. Actually, we debated before we started. So for a switching model, I think this is my personal opinion because our team created this approach. The switching dynamics should be modeled only when you're developing power electronics devices, because what we are trying to do is looking at these devices from system level. That assumes your power electronic design is feasible, is viable, meaning your switching frequency should already met the technical consideration I gave you, right? So in that sense, what my assumption when we're using average model is your device follow the design perspective. And then they will give me this value on average, the performance, right, at the microsecond level. So we just assume if we gave you this kind of, for example, the power level control signal, and then you will give me back this this performance, that kind of thing. So if you're simulating, for example, designing a new power electronics device, then you should go down to that model. But from the system perspective, I don't think that is necessary. You should prohibit the people from doing that, because what we're trying to do is to assume a device works, then whether or not that they can be scaled up, and what's the impact to the power system operation.
Thank you for answering my question, Professor Lu.
Okay, so Ning, I think I just want to sort of put your presentation in context with our experience. So if you have this small microgrids with a lot of PVs and so forth, and you really want to have high quality of service, like, you know, to meet quality of service, whatever, you know, the specs are, you face this problem about how can you actually do it? Because when PWM starts switching, you get a lot of harmonics and stuff like that. And the way people fix it, as you said, you put the ground transformer to get rid of DC level, and then you have to put a lot of hardware, low pass filters, high pass filters. It costs money, you know, the putting all that hardware. So what we are working on is really this trade-off between how much hardware you need to clean these signals versus just being a little smarter with filters, with digital filters and control. Do you guys have any experience with that?
Our students actually at Victron Bay, they spend a lot of time on that. And I think what my opinion on that is there are two ways of doing that, because one thing we can do is from the energy and power management level to schedule the energy budget more precisely for that particular interval. So if we can already maintain the balance of the load and this PV power and then the variation, we could effectively control the ramping and then the variation. So by doing that, we would put our power electronic system in less stress. But from the power electronics perspective, how much they can handle would be able to translate into a power constraint, like how much you can ramp up, how much you can handle instantaneous load change, and then how much I can handle the imbalance between phase A, B, and C. So right now, what our approach is, our power electronics team will take the current state of the art, and then we have this microgrid controller, and then we will put in the system and see if it works. If it won't work, then we will restrict our control for power and energy, and then to see if it works. But it will still not work, then the power electronics team will, the HR team will develop a new function, like we have Victor develop this power following capability for PV. So that will give us flexibility to handle from this source level how much we can do. And then we also designed this detailed diesel generator model so that we can have a combination of synchronous generator plus the PV that can be regulated, and plus the storage, and then add in this the ground transformer. But we also do this without this grounding transformer. Then what's the problem? So we know that even without the grounding transformer, what we have been literally have to achieve is to maintain the power imbalance between the space to be 0.3, right? So that means it will put a higher requirement on our energy and power management algorithm. Does that make sense?
Absolutely. And there is Rupa Mati Jadivada here, our postdoc in RLE at MIT. I mean, she's spending a lot of time on, even if you do that, I think we don't have very clear specs. It depends on which level of granularity I say. There is no very clear industry spec now and standard of how much frequency deviation you would allow, how much voltage deviation you allow in these new power electronically things. So it is just like, okay, you align power imbalances, but at the same time, somebody looks and says, oh, well, this design is not really that good because, you know, you have some glitches or some high frequency oscillation in your frequency, but it's still within the band of 0.1% or something. I think that we are really working hard. I've spent a long time now, 10 years on, can you have simple extensions of like area control error and things like that for the different granularity, so that if you put the specs and specs understood, they don't have to be the same for every technology, then somebody who is putting this system together or in the interactive way, they can decide if they can meet the system level spec or not. So I would say that my general comment to what you were talking about today, it's, you know, there is this sort of more system theoretic control and modeling approach, and then there is a lot of data driven stuff, and those have to somehow meet somewhere. You know, it's very easy, for example, and I can't put them in my head. One thing is, okay, I use my standard two-loop inverter control, and I can easily show you that if you do that and you have operating conditions change fast, I have a voltage collapse. So what? You know, what do we do then? And how do you change the controller so you don't have that? So I think there is a lot of sort of hidden low-hanging fruit for better control. So the question is, how do we convince now the vendors, technology developers of these new inverters to actually go into next generation so that everything else the same, they perform better, whichever way we are going to measure it better? Or are we going to always have the same control and then try to see if it's good or not?
Yeah, so that's exactly the reason
really,
we have this kind of simulation. Yeah,
I think it's really a turning point in the industry, right? Because you can go both ways, but you have to have some incentives and some standards too. I think it's great, you know, that you are creating this multi-scale digital twin, and you know, that is being happening at other places also. But there are also a lot of questions, but very technical question on data versus physics-based modeling I have, because Tong is somewhere there. He's still there. We just had a really nice experience that tells you everything. If you look at input-output transfer that you want to model with a lot of data, right? You model it and say, okay, this is my good model for whatever I want to see how is the power going to change out of the droops if I change the set point for the governor, let's say, or for the inverter for frequency. And you do all of that, let's say, secondary level into slower time scale, and you get the model, looks beautiful, it fits nice, the data. And then you realize that your model actually didn't have that data-based experiment, didn't have sufficient excitation and the input to discover effect of something that really matters. In this case, the effect of load fluctuations, and you get completely different answers. So I really think that some validation of, we've gone through this before with adaptive control long ago, is that unless you have, this is how it comes from the control's point of view, if you don't have sufficient excitation in your controller, you can't control, things will fall apart, right? You think that they're going to work, but you test all these adaptive controllers and then put the actual input and things are unstable. So I think we have the same problem with data. What is the sufficiently realistic model that you are trying to fit with this data at different level of granularity? I think it's quite an open area as far as I'm concerned, and I don't see very many people actually looking at it. Any comments on that?
I think based on our simulation result, because what we basically are treating our HIL, the high resolution simulation is like a real system. So we can put that information out to our control system and then using this as a model to forecast what the future behavior is. So my thinking is you don't need, for the physical layer model, you need as detailed as you can. But for the control level model, you don't really need highly sophisticated data set, depending on how faster you can access your measurement data. So if your measurement data is updated, for example, every minute, right, then you're probably having a simple model. But if you're accessing this data every 15 minutes, then probably you need to use a first order or second order model, because it can no longer use a persistent based model to give you an accurate result. So my question to my answer to this question is, if you are designing a physics-based model, like the model we're using in our HIL test system, we use as detailed as we can go. We use the manufacturer data and then the field testing result. But inside our controller, that model would be simpler, because it is a reflect of what is happening in the physical layer. And then if we access this model real quick, then that model complexity can be simpler. But if we only access this model every an hour, then probably you need a more accurate model to actually faithfully represent what this physical layer would evolve. So I don't know if that answers your question in a way.
Answers in part, but you know, when you were talking about going and sampling faster to recover what's in between, I don't think that's always doable, because
that part is different.
So
that part is different, because that part of what we're talking about is basically whether or not to move a model from the microsecond level simulation to millisecond level simulation. So what happened is that there's a delay because your millisecond level simulation would not see what will happen in this process, because the next communication interval will probably be 10 milliseconds later. So if you have you can use interpolation to interpolate a few values in between. It can reduce the amount of discrepancy there. And then that will actually help you to improve this level of, but there's only a certain thing you can do. For some dynamic, this, even you use interpolation, it may not be sufficient. But this kind of method gives us a method and a performance metric to see what model can be moved from EMT to the phasor domain. So we do this benchmark first, and then decide, okay, this is not going to influence our control. Then we move that to the phasor domain. Victor basically is doing that work. So Victor, do you have any comments? If you want to just add a few things that I'm missing.
Hi everyone, this is Victor. I think one of the main contributions there in that work is that we run some scenarios in a co-simulation environment and see how much we can actually be moving the devices from one domain to the other, and how much do we lose. This is an area that definitely needs more exploration in the field, and the more results out there in this topic, the better we will have an understanding of what we're losing when we're moving devices in between. And since our grids are moving to having a lot of these distributed energy resources with inverter-based connections, we will need tools that can simulate part of the system in a phasor domain, so that we can simulate more devices in a co-simulation setup.
Okay, I understand. Thank you. Any other questions? Comments? Okay, I think, Ning, I think it's 12:15 now. We very much appreciate it. It really was very good. Okay, I think here is one more quick question, I think.
Sure.
Danilo, you want to introduce yourself and ask the question? Danilo?
Sorry, yeah, I had to unmute myself. Hello, everyone. So my name is Danilo. I'm a PhD student from KTH visiting at MIT. So I was wondering, when you were discussing this mismatch, when you're switching from model to model, how do you quantify that mismatch? How do you say, okay, this mismatch is fine, this one is not?
One simple way is to conduct this benchmark testing for typical operation conditions, like what we presented in that paper in that slide. So you basically move things over from the EMT domain to the phasor domain and see what the discrepancy is if you use this level of delay or if you don't use the interpolation. But there should be
I think the question is over which time, in which norm or whatever. Is that, Danilo?
Yes, exactly.
It's really what, I think it goes back to this crazy question about not having the standard for measuring the, I think we discussed it just a little earlier.
I think we designed some benchmark tests so that it would characterize the ramp rate, for example. And then for the large, say, when we put the microgrid in operation, the peak lock loads by different groups. So if we do those extreme situations, then we capture most of these scenario right already. Because what we are trying to do is to see, well, you can do this, you can pick up a load group, but up to which power level we can do that. If you show me, say, 1 megawatt at a time, will that bring the whole system down, right? So if it's not, then we do 2 megawatt. So that way we would be able to provide this energy management team a constraint. Say, if you guys want to control your reconfiguration decisions, then make sure each time you reconfigure the whole feeder, the new load group you throw into my microgrid will not make me exceed that power level, the ramp rate. So this way we can also use this kind of a condition in these tests to see if such case is often happening in this, then whether or not we move this from the EMT to the phasor domain, that will crash the whole simulation. I think that's one way of doing that. But I agree there's not a systematic way for us to say, these are the industry agreed standard testing, right? I think that's Maria, what you're trying to do.
Yeah, I'm saying that, but I'm also saying that with a lot of intermittent inputs, right? I don't think that we know any longer what's the worst case.
Well, for us, there it will be because when we are doing this sort of like a simulation, we have our use cases. And then
but I think in real world, you take it to real world, then you assume that this was worst case, but it's something else.
Even in real world, when you operate this microgrid controller, right, you have your energy control and power regulation. This whole thing is a limit in that algorithm. For example, our algorithm eventually capped the power we can switch on and off to meet this microgrid detected level. But the simulation, this is another level. It's like one is the equipment defined level, one is the other is simulation limited level. Meaning up to this kind of simulation, I can no longer separate these model between the, we can no longer put this model into the phasor domain. We have to model everything in EMT domain for us to achieve the highest accuracy. So I don't know if that makes sense. But the other thing is once we model the whole thing here, but physically my control limit is reached. So no matter I model that in the EMT or with EMT and the phasor, it will all fail. So that would be a hard limit. So the other one is a modeling limit. One is the hard limit put on there by the equipment. I don't know if this explanation makes sense to you.
I think we have in our research sort of given up on the worst case thing. You can maybe establish some bounds on the right interface variables, but within those bounds, many things can happen, you know. So like adaptive controller may work, constant gain controller may not work. I think there is a lot of stuff that's going on under the.
We try to avoid those surprises because that's the way we were using this digital twin to test our controller to see if there are cases that our design didn't consider so that it would run it out of limit. Because for example, I said when we didn't consider those, we actually have it running on the HIL because it has a dynamic and then also have a communication delay or everything. Then if we don't control that all right, then we could run our battery 120 capacity out of their rated power. Why is that? Because in our energy and power management system, we do every 5 minutes of forecasting and then control that. But within that 5 minutes, the load could jump up, which the forecasting cannot capture. So if that happens, what you would do? There's nothing that this kind of energy management can do anymore.
So here let's close it by this. I had the major question at the beginning. It's wonderful what you're talking about. It's a lot of good, great work. But, you know, I come from, okay, what is that I don't know? And one thing is throughout the whole conversation, presentation, you were talking about you. Is that the EMS? Is that BMS? Is that the component? We are beginning to differentiate between different players, you know, and they have to do their different details at their level, and then maybe exchange less granular in between or something like that. So there is no you. Do we agree on that?
I'm not
Your
too sure.
digital twin is still trying.
So here, I think I didn't present the EMS part or the power management part because today I just skipped that part. But we do have a layer which we model externally. Model this energy management system like a microgrid controller, and that controller actually model the energy management and the power management. So the energy management that models like 24-hour ahead, and then schedule every hour what's the energy should you keep. And then there's at real time there's another one.
That is not what I'm talking about. These management things exist. The question is when you test your hardware, you know, you don't know the details. Somewhere down in the branches of the distribution system, somehow the energy management system at DMS at least level should know that information in an online environment, exchange it, because it may change as conditions change.
There's something that the EMS system will never know. So that's why we distinguish device level control and then the microgrid, the system level control, because all this instantaneous information has to be responded at the device level. There's just not enough time for you to actually communicate to the EMS and let it respond to it.
This is why we are going into distributed multi-layer, but I suggest, and I think we are going to push it from the MIT side. I really enjoyed listening to how much work you guys are doing at North Carolina, and I visited there several times. So I have great respect for what you're doing. I think we as a community should donate challenge problems. Like you talked about everything that works so beautifully, but you never told us what is the challenge problem that only if you solve it now, there is a major milestone. We have, in our pockets, a set of challenge problems that some of people here, like Rupa or Danilo Mislav, they don't really want to hear, or Dan, because we spend so much time on how do you resolve those challenge problems. So I think at the end of the day, the question is, and in the past industry, things were simpler, so there were not these challenge problems. So what are the ones that matter really at the end? What is that we have to resolve absolutely so that these new systems work? And to create the challenge problem, say, if you resolve this one, like, whichever way you are doing it, then, the industry will feel more comfortable adapting something or changing something. I am thinking about that a little bit, and maybe we'll do some. I've talked with NSF about possible workshop on such type of brainstorming. So please think about challenge problems that you want to share with the community. And there is really only a handful of people that is really working seriously on this, but it's very new. It's very new area. What you are talking about, we had just these, focused, function-dependent computer applications. Now you have to put them all together with different granularity. I mean, the magnitude of what needs to be done on this digital twin is really overwhelming. So there must be challenges there. So let's share those. Thank you very much, Ning. I really enjoyed it, and I'm sure that everybody else did. Is there some last-minute question that I'm missing here? I guess not. So thank you.
Thank you. And then thank you for staying this long for the discussion. I really enjoyed it. Maria, thank you for the invitation.